Perfect. So good morning. My name is Joost VandeVondele, and I'm the Deputy Director of the Swiss National Supercomputer Center, CSCS. We were already mentioned a few times by Martin and Imanol. We basically provide the infrastructure that is at the basis of Swiss AI initiative, and I would like to introduce in two steps what we do for the initiative of machine learning at scale. First, give a little bit of an introduction of the center itself, and then go a little bit deeper on what it means actually for the center to be able to deliver these large language models, some of the experiences that might also be interesting for you to see how you interact, for example, with the centers where you train, or what kind of difficulties we've faced and how we've solved them. So first of all, this is the mission of CSCS. It's basically the goal of developing and operating an infrastructure that serves both compute and data needs to advance science in Switzerland, to produce world-class science in Switzerland. We've been doing that for a fairly long while. It's a research infrastructure that is not isolated. It's connected to experiments in Switzerland or worldwide. For example, we process part of the data of CERN, or we are connected to some of the largest telescopes in the world that really produce very large-scale data. We also have experience with operational services. For example, the National Weather Forecast is one of the critical services for the country that actually runs at CSCS. It's also the case that we have infrastructure in Switzerland, but we're also having infrastructure, a share of the large supercomputer that is located, for example, in Finland, Lumi supercomputer that some of you might have access to. And then we have a user lab that has been producing scientific output for many years. This is just shown in that graph up there. You can see that these numbers, they happen to go to 2021. They have only a very small bit of computer science in there. It's mostly natural sciences. I would say that is now the moment where this is changing. A lot of the work being taking place in AI and machine learning is actually happening in the computer science field, and we're very happy that we're part of that development. Now, we actually have a lot of experience, and I think that is why Switzerland is so fortunate. We have been adopting GPU computing as the main technology for HPC back in 2011. We have been working together with, in this case, NVIDIA, with their early hardware, and we were, for example, the launch customer, so the first large customer of the P100 GPU nearly 10 years ago. And we've also been one of the first centers that were able to push GPUs for operational weather forecast. And also that was an achievement. And we've taken along a whole community. Now we've kind of repeated that in 2024 with ALPS. Also, that is one of the largest computers in Europe for open science. So the numbers have been shown on the top 500 list. It's not so important to us, but enabling open science at scale is crucial. And again, we've been working very closely together with our vendor partners, which is HP and NVIDIA, to be the launch customer of this new chip. So the Grace Hopper, the Grace Hopper super chip, which is basically a tightly integrated CPU and GPU. And that, if you develop and deploy new hardware, always comes with challenges. I will go into that. And that collaboration is key to make that happen. So what is ALPS from the infrastructure point? It's actually a bit broader than what I present here. So it's a varied hardware, but predominantly it's the Grace Hopper super chips, of which we have more than 10,000. They're organized in nodes, which have each 4 of these Grace Hopper super chips, and then they're connected with a high-speed interconnect. So 4 NICs per node, each of the NICs 200 gigabit performance, allowing us to train, as I will show later on, at scale with good performance. Now, one question is also, what is actually the power usage of the infrastructure? First of all, quite a few of you might have come by train to this meeting. That's a good measure. It's about 2 trains, 2 locomotives that consumes roughly the same as one of the largest supercomputers in Europe for open science. So if people tell you how much power do you use, well, roughly as much as the train you took to work this morning. That I think is very important as a measure. It's still a lot of power, and we are proud that we work on this to use that as efficiently as possible, We have a data center that is water cooled. We have electricity that is carbon neutral. We use hydropower only to power the center. Now, what is also important is that we want to go beyond this GPU supercomputer. What we think is actually the future, or the next step in our infrastructure, is what we call this cloud native supercomputing. That is the observation that we need much more flexibility these days than we had with traditional, single vertically integrated supercomputers of the past. We've invested a lot of effort to make ALPS an infrastructure, software-defined infrastructure that we can flexibly partition, that we also can customize for various users. And that's kind of what we show in this graph there. It is one infrastructure, but it serves a multitude of domains. We have a platform with the services needed for, I would say, traditional simulation-based science. We have platforms that serve data processing for CERN, have, the telescope data. But of course, one of the main platforms these days is the platform for Swiss AI, which is the machine learning platform at ALPS. We've documented that. You can read on these papers what this means, the concepts behind that, what kind of efforts and services we are developing, making possible to actually do machine learning with support, not just raw compute. But in this community, I think this graph is very well known. We know that infrastructure is key for modern AI. We have the scaling laws that basically says that provided sufficient data, compute is what you need to have low loss, high accuracy. And we have this staggering evolution in the flops needed to train, advanced models. And we see that this is growing at the rate of, 4x per year. And that, of course, is going to be a challenge, no matter what kind of infrastructure you have on the floor. Now, engineering the infrastructure, I want to share what I call today the status of that infrastructure. But then maybe some of the more interesting slides are going to be on, how hard was it to get there? And that's what I want to share. Now, I've had many sleepless nights over the past year because it was truly challenging journey to get that machine running. We got the hardware January 2024, and I would say roughly in January 2025, we declared operations for all our user programs. And only in about, I think April, it must have been, or maybe later, May, we had this graph. And then that was the graph that, improved my mood significantly. That was a comparison on the right of the training of the 70 billion Patus model, or, whatever the name is going to be, on the ALPS infrastructure, where you see very stable performance. That was very comparable to a graph that Llama just published on the left for, the 70 billion Llama model, kind of similar models. And you see that, the right picture that we refer to as a Swiss watch. So very nice and stable performance. We could analyze the data. What's the checkpoint? What's the garbage collector? And so at that point, I realized that our infrastructure is maybe not of the same quantity as, the huge centers that some of the commercial providers employ to train, but it might be of the same quality. And I think that was a very important message. Now, what does it mean for the performance? Imanol mentioned already, the 780 tokens per second per GPU for the big model at scale. You can do a bit more conservative estimate, not just take the peak performance average of a larger graph. That's what's shown there. It's both strong and weak scaling numbers that we collected over the weekend. That shows that, we actually have good parallel efficiency up to about these 4,000 GPUs. It's dropping a little bit, maybe 90% efficiency, but that is still very good. The other thing I am very proud of, that is what I've been watching as an open tab in my browser all the time. How good is the full initiative and not just this model using what we call Clarity, that's the machine learning platform. And that's a graph for last week, basically. You see it's nearly 96% of all resources that we offer is being used, and we are able to deliver 95% of all resources, all hardware in good shape to the users. That's very good, and that you can see in that right graph, that's Imanol's weights and biases. You see perfectly straight consumed tokens over time. If that were the sole reality, I would take a long break and just enjoy. But that is actually the reality of, if you don't select data, that looks just good, which you might do for a publication. So on the left, you see 30 days, and you see, the kind of things that happen in real life. You say, okay, at a given point, we develop and operate the platform. That is, we don't keep it stable. We need new features. At a given point, we want to train medical data. That is, we have to have better partitioning on the system. We need to upgrade the system management stack to allow that. That is one of the big orange slots. We make a minor version upgrade, system goes down, we need 2 days to recover it. The other big upgrade, okay, we have a water-cooled infrastructure. You need to clean the heat exchanger at least once per year. System goes down, you use the opportunity to do a major upgrade. Oh, that turns out to be 4 days of work to recover the system. And then, this weekend, Saturday at 10, I was, happily at home. Suddenly the message, we've lost the center, the pumps are down. I looked at the Meteo Swiss app, lightning strike, Lugano, big thunderstorm. And the whole weekend was basically spent in trying to recover, giving priority to the community. And so we got them back running on Saturday evening or Sunday. The other thing that you see is, this is weights and biases for real. You see the lower half, the runs are actually, we have 20 runs that take all, that last all only for, 10 or 20 minutes, till one node that, evades detection is actually identified by a human. And then you're back in the nice cadence where jobs run for hours. But we have to learn, how do we find that? What are the metrics to, detect this kind of failed hardware? It cannot just be a human, you have to automate it. The other thing, which I'm sure is different from how large centers, like think OpenAI, Google, do their machine learning. We have this AI initiative with about 500 users that all want to do, a different kind of thing, not just the LLM. They want to train some video models. They want to do something of this. Very different workloads. They have support requests, 500 people that ask, how do I log in? Well, please read the documentation. But we have, more than 2,000 users in different fields. This is one of the projects we handle. And so far, we're basically supporting infrastructure, engineering infrastructure for all these projects. And we have to handle that. And if you look at the numbers in literature, what's the kind of engineering effort to support, the development of an LLM? Even for smaller models, people say it's about 20 FTEs. If you go to multimodal models, you would need a team of 50. And that's roughly how it feels. So we have that like many people that look at all elements of the stack. The users might not notice when the pumping station goes down and not know the details. They will notice, but that certainly takes people, that manage the facility, that have to drive down to a pumping station, reset an infrastructure, or all this kind of aspects. And then the other thing I want to show, and again, going to use Emmanuel's weights and biases here. It's a bit hard to read. Upper graph is the performance of the LLM training in tokens per second, and you see it drop, and you say, hey, why is it halving the performance? And then it takes some time before somebody says, let me look at some of the storage dashboards, and you see, oh, our storage servers have this strange behavior, and it turns out a different user in a different community is kind of misusing the storage and basically overloading the storage. And now we see this cross correlation, and you have to talk to a user in a different community here, climate, which is one of our important communities. So I spent quite some time in developing, a little script that helped me push, this message on the importance of what's going on in the center, trying to find a middle way between the typical engineering monitoring, where they just look at, the hardware, to also making predictions. When is the LLM going to finish? And I'm going to move here. Like, for me, the 15 trillion tokens, it's this one here. I predict 23rd of July, you're going to have that 15 trillion tokens available. Yeah. That was partially for your birthday. But what I also see is that some of the things that we usually measure or that we find important is like, how well does the model scale, or how much do we gain in tuning this parameter or writing in CUDA? Is maybe not as important as for the ultimate delivery. So we monitor how long can we keep that job up? Like, are we giving it 100% runtime? And right now we have 93% in the last 2 weeks. So that's pretty good. That's not where we want to be, but it's 93% of the time we have that big job running. What is not so good is the mean time between failure for a run. Like in this graph, it's 3.7 hours. Now, the metric is not perfect because we have this one case, for example, where a job dies 10 times in a row after 10 minutes. So we also look at how long the longest job would be. And as in this case, it's like 2 days of uninterrupted running at 4,000 GPUs. It's possible to hit that once. But then this is important because we allow to measure the real throughput of these models on the infrastructure. Here, it's not the 780 that Imanov probably shouts, but over these 2 weeks, it's about 550 tokens per second per GPU. And I think it's very important to look at that. It also allows us to estimate the cost, because we have a cost at operating that infrastructure. We reserve part of the machine for that high priority project. And you can try to read these numbers from far, but it's in the millions. And it allows us to predict, I have many more slides. It allows us to predict what it would cost to repeat this exercise. Yeah. Let me go quickly. Very important messages. It takes actually, 4 to tango, not just 2 as ChatGPT will tell us. You have to have the vendors, the user community, and the center work very closely together. We have had bugs in all components of the software stack that require the expertise of all 4 to resolve. Now, finally, some thought is if this open source community wants to remain competitive, that is kind of the scales we have to keep in mind. Like today, Ops was about 0.1 billion investment, partially because we were early enough. The value is maybe 0.4 or 0.5, but still you have to see it in the context of investments of the order of 100 billion. And I think that is very important. That allows me to conclude that I think, we can deliver value for this open source ML community. A lot of this is engineering, it's not just the hardware. The hardware was the easy part. And then for this community, I think the cost of these efforts is so huge that you have to amortize this cost. You have to reuse, to collaborate, and actually be smart. This is the place where we can innovate, and I think that is kind of your talk. Good, I'm going to keep it at that.